Our next speaker is an expert on bioinspiration. Professor Shinya Aoi received the bachelor, master, and PhD degree in engineering from the Department of Aeronautics and Astronautics in Kyoto University in Kyoto, Japan, 2001, 2003, and 2006, respectively. He was with Kyoto University from 2006 to 2022. However, he is currently a professor with the Department of Mechanical Science and Bioengineering at Graduate School of Engineering Science at University of Osaka, also in Japan. His research interests include dynamics and control of ledger robots and analysis and simulation of locomotion in humans and also animals. He received the Young Scientist Prize, the Commendation for Science and Technology by the Minister of Education, Culture, Sport, Science and Technology from Japan government in 2017. He also received the Best Paper Award at the International Conference of Biomedical Robotics and Biomechatronics in 2012 and in the International Symposium of Micro-Nano Mechatronics and Human Science in 2018. So, Professor Shinya, welcome.
Okay, thank you very much for the introduction. I'm Shinya Aoi from the University of Osaka in Japan. First of all, I'd like to thank you for giving me the opportunity to attend this conference and also give a talk. And today I'd like to talk about the Gait generation of regular robot through neuromechanical interaction and bifurcation. And first, I'd like to introduce myself very briefly. And I'm from the Department of Mechanical Science and Bioengineering at the University of Osaka in Japan. And my study includes biomechanics, robotics, and system engineering. And I received my PhD from Kyoto University in Japan, and I moved to Osaka 2 years ago. And the University of Osaka is located here, here. Osaka very close to Kyoto in Japan. And this university is founded in 1931, and this university has almost 23,000 students and 3,000 teachers. And also it has 3 campuses like this. I'm in the Toyonaka campus, I'm in the middle one. And my study, especially focusing on the adaptive and agile locomotion in terrestrial animals. And these animals, including humans, walk in diverse environment. Humans walk easily even when there are stairs, and this goat walk on a very dangerous and steep cliff. And also left down movie shows dog sports called agility, where dogs run through very complex obstacles. And this cheetah has very excellent physical ability and run fast to catch prey. And animal locomotion is generated by skillfully manipulating the complicated, very complicated, and redundant musculoskeletal systems. And it's achieved through dynamic interactions between the brain, neural system, and the body, musculoskeletal system, and the environment. And this concept also applies to underwater animals. And we especially aim to elucidate this mechanism in terrestrial animals and apply it like the robot. And in particular, we're focusing on three approaches based on animals and models, and also robot. Specifically from the, sorry, I'll prepare the, it's okay. Specifically from the major data of animals, we extract characteristic structure embedded in locomotion and make hypotheses about the locomotion dynamics and control. And then we construct mathematical models and reconstruct locomotor behavior through computer simulations to evaluate the hypothesis and also to clarify the mechanism of locomotion in animals. And finally, based on these findings, we developed a robot to produce adaptive and also agile locomotion in the real world. And I'll show some overviews of our studies. The first is about human walking and running. As you know, we change these gait patterns depending on the speed. But these gaits have many differences. For example, during walking, at least one leg, one foot is always in contact with the ground. In contrast, running has a flight phase where both feet are in the air. In addition, walking is generated like an inverted pendulum, but running is generated like a spring. And to create such different gait in humans, a motor control hypothesis has been proposed. Specifically, a linear combination of 5 sequential signals explains the motor command for muscle activity to walk and the change in the second signal, change walking to running. And to investigate this hypothesis about motor control, we use a very simple neuromechanical model, especially neuro, muscular, and skeletal model, like this. And through computer simulation, we investigate and achieve gait transition from walking to running, like this. It's very simple simulation, but from the walking, it actually achieves running behavior. Okay. And also, there is a very special device we call a split belt treadmill to investigate adaptation mechanism in human and also animals in locomotion. And specifically, it has 2 parallel belts, and the belt speeds are controlled independently. Therefore, this treadmill can create left and right asymmetric environment for walking. And especially when the speed is different between the belt, this is human walking, the relative phase between the left and the right legs shift from an antiphase, like this. We can adapt this kind of the very special environment. And also to investigate this adaptation mechanism in humans, we performed computer simulation of a neuromusculoskeletal model like this. Tide means the same speed between the belt, and the change to the split belt. Split belt means the left and the right belt speed are different. But this model can adapt to the environmental change from the sensory information and the motor sensory coordination. And not only this model simulation, we apply our findings to a bipedal robot like this. And tide means the same speed, and it changed to the split belt. I mean the different speed between the belt. And this actually shows adaptive behavior during split belt treadmill walking. And not only humans, but also quadruped animals such as cat also show adaptive behavior in split belt treadmill walking. Therefore, not only a bipedal robot, we also use a quadruped robot to investigate adaptation mechanism during split belt treadmill like this. Now it's split belt. Okay. And also, we humans have achieved bipedal walking through evolution. But the origin remains unclear. On the other hand, these Japanese monkeys can achieve very excellent bipedal walking through training like this. And this Japanese monkey is a very useful model to understand the origin of human bipedalism. So we also construct a neuromusculoskeletal model of Japanese monkeys like this. And we performed computer simulation to change gait pattern from quadrupedal to bipedal from the dynamic viewpoint. And also, we applied finding from the neuromusculoskeletal model simulation. We applied a bipedal similar to the previous case, like this. First, walk quadrupedally, and stably change to a bipedal walking. Sorry, it takes time. Yeah, like this. And we investigate the animals and the models, the computer simulation, and apply to robot. But today, I especially talk about two topics. The first is about gait transition in quadruped robot, to investigate why quadruped animals change their gait pattern depending on speed. And the other is about maneuverable locomotion in many-legged robot. Many people do not like this, but this is to investigate how many-legged animals produce their maneuverable locomotion using many legs. So first, I'd like to talk about this first topic about quadruped animals. And quadruped animals change gait pattern depending on the speed, similar to human walking and running. But humans move the left and right legs in antiphase during both walking and running. But quadruped animals change gait pattern by changing the phase relationship between the legs in a very different way to humans. In particular, they use walking at low speed, like this, where each leg moves independently, like this, not synchronized. But when they walk at middle speed, they use trotting. In this gait pattern, diagonal legs are synchronized like this. Very beautiful. But when they walk at high speed, they use galloping. We can see in the horse race. In this case, left and right legs move almost simultaneously, like this. However, the mechanism of the gait change in quadruped animals remains largely unclear. And I'll show a movie about the experiment of this cerebrate cat. In this cat, a portion of the cerebellum is removed. And the body is fixed and supported by this device, but the legs are free, and the feet are put on the treadmill belt. And when the belt speed moves like this, then this cat begins to walk like this, in the absence of cerebral function. In addition, when the belt speed is increased, this cat changes gait pattern, especially start running like this. Because the spinal cord is intact in this cat, this suggests that the gait transition is induced by local sensory feedback from the feet. So we aim to investigate this gait transition mechanism induced by sensory feedback using a very simple quadruped model. And this is a very simple body mechanical model composed of one body and four legs. And each leg is connected to the body by a pitch joint. And leg length and the joint have springs. So it's very simple structure. And this figure shows a neural control model composed of phase oscillators. Each leg is controlled by one phase oscillator. And this phase oscillator produces the desired leg motion like this by controlling the leg length and the joint angle like this. It's a very simple equation. And this leg motion is controlled by springs with a desired motion similar to the PD, the proportional and derivative control in robotics. So it's very simple control. And the neural system receives sensory feedback. Especially, each oscillator receives actual leg length. Just this information. And the phase, we use the phase oscillator for the controller. And the phase dynamics of the oscillators consist of very simple one. Only the basic gate frequency and sensory regulation, just the two terms. And we use the error function between the desired and the actual length to regulate the locomotion rhythm in the oscillator dynamics like this. So this is also very simple equation. And although this model has 4 independent oscillators, but we fix the left and right legs in antiphase. In this case, the gait pattern is determined only one parameter, very simple. Especially the relative phase between the fore and hind legs. In particular, walking pattern is generated by pi over 2, like the left one, and also the trotting at the middle speed is generated by pi, like this. And using this very simple quadruped model, we perform the computer simulation like this. As a result, when the gait frequency is large, so very fast, then the walking changes to trotting like this, without changing any parameters. Yeah, now it's walking, and around here, change to trotting automatically, without changing any parameters. In contrast, when the gait frequency is small, in this case very small locomotion, then trotting is changed to walking automatically without changing any parameters. And here. Namely, different gait transitions appear depending on the gait frequency. This is the result, but we want to know the mechanism. So we investigate the mechanism of these gait transitions under the assumptions. The body rotations and also leg joint angles are small. Because the left and right legs move in antiphase, at least one leg is always in contact with the ground in both fore and hind side. So the equation's motion of the center of mass height is given like this. It's very simple. Just acceleration and the force and gravity. And by regulating this equation, we obtain this like this. In particular, this omega n explains the natural frequency about the center of mass height. And in this equation, we obtain the stationary solution like this. It's very simple type. And based on this stationary solution, we obtain the phase oscillator dynamics like this. Also, it's very simple, just using the two terms about the basic oscillator frequency and the sensory regulation term. And we obtain this using the stationary solution, x hat. And by using the relative phase, this delta, then we obtain the governing equation of the relative phase. And especially the right-hand side, the sign of the right-hand side changes depending on which of the natural and gait frequencies larger. And pi over 2, namely walking in the blue, and also pi, namely trotting, are both the equilibrium solution of the governing equation of the relative phase. And this indicates that when the gait frequency is small, walking is stable and trotting is unstable. And this induces a gait transition from trotting to walking. In contrast, when the gait frequency is large, then it changes to trotting is stable, but the walking is unstable. And this induces the gait transition from walking to trotting. So completely opposite. So we obtain from the dynamical analysis about the stability and why gait transitions appear and why different gait transitions appear. So to verify this result in the real world, we developed this very simple curbed robot. And we confirmed that when the gait frequency is small, the locomotive behavior is not so good, but actually the relative pace change from trotting to walking like this. This is the case when the gait frequency is small. And in contrast, when the gait frequency is large, then the gait transition change from walking to trotting like this. So it's completely opposite result. And we verified the result about the dynamical analysis using the actual robot. Okay. So next, I'd like to talk about the second topic of the many-legged locomotion. Using many legs like centipede provides the ability to avoid falling down and tread leg damage. So it would be useful for legged robot. And the centipede arthropod with a pair of legs on each body segment. And they have at least 15 pairs of legs, and sometimes more. And they flex their body segment and move their legs, generating body undulations. And they change the gait pattern depending on the speed, similar to quadrupedal animals and also humans. Specifically, body undulations are usually absent at low speed, but appear at fast speed. And amplitude and wavelength increase at the speed. So please watch this movie. Resolution is not good, but I think you can confirm that the centipede change the gait pattern depending on the speed and produce very large body undulations at high speed. However, it remains unclear why they create such body undulations, because they have legs unlike snakes. They do not necessarily have to produce body undulations. And actually, there are biological conflicting hypotheses. The first said that they actively produce body undulations. And the other said that they resist body undulations, but fast walking creates these undulations. And in this study, we especially focused on the second one. They do not want to create body undulations. So to investigate this, we especially developed a robot model composed of 6 body segments and 12 legs like this. And the body segments are connected by yaw joint with torsional springs to resist body undulations. And we performed computer simulations like this. Then this robot walks in a straight line at low speed, and also with high spring stiffness, namely the low spring compliance. However, body undulations appear at high speed and also with low stiffness, namely the large compliance like this, similar to centipede. Because we use just spring, we do not motor about the body axis. This is just a result from the passive dynamics. And to verify this computer simulation result, we also developed a centipede-like robot like this. And this robot walks in a straight line at slow speed and with low spring compliance, similar to the model simulation, just walk in a straight line. In contrast, body undulations appeared at high speed and also with high spring compliance, similar to the model simulation. And also, this is just a demonstration, but also the robot walked in a straight line at low speed and with high spring compliance. Body undulation appeared over critical value. In particular, the amplitude of body undulations increased at the speed and also spring compliance increased like this. So, sorry, just that. It's okay. And this result means that the split walk is destabilized at critical value by increasing the speed and also spring compliance. And the body undulations of the robot are generated by hop bifurcation. And also, when all the spring compliance was increased, the body undulations appeared by hop bifurcation. But when only the spring compliance of head module was increased, straight walk is changed to curved walk by pitchfork bifurcation, namely the different bifurcation, like this. And also the curvature depends on the compliance, like this. And this movie shows the curved walk with very small curvature like this, without changing any parameters. And also the bottom movie shows the curved walk with very large large curvature. We do not use any reference such kind of the curved walk. This is just a result of the dynamics. And also here we discuss the centripetal locomotion again. In this movie, only foot contact points are shining. Okay, you can find that. They are shining. And also, these yellow circles show the foot contact point at the moment. And this means that many legs are in contact with the ground to support the body during locomotion. And also, these legs are constrained on the ground because they support the body, and which can make maneuverable and agile locomotion, such as quick turn, difficult. But the actual centipede show very maneuverable and agile locomotion. Namely, the mechanism to produce maneuverable and agile locomotion using many legs remains largely unclear. And not only the centipede, also you do not like this, but the cockroaches. It's not actual, well, just I like draw. Cockroaches also show very maneuverable and agile locomotion like this. And there is, to investigate the dynamics of the cockroach locomotion, very simple model, right one, has been proposed. And this shows that the straight walk stability change depending on the position to receive the ground reaction forces, like this. And when the straight walk is unstable, the model cannot continue straight walk like this. I mean the right part. But by comparing a quick turning task between the stable and unstable cases, we found that the straight walk instability help maneuverable and agile locomotion like this. I mean the very quick turn. And as well as cockroaches, aquatic animals such as sea lion also suggested to use instability to enhance maneuverability. In addition, not animal, but fighter aircraft such as F-16 are designed to be aerodynamically unstable to improve maneuverability. And because our robot also has a straight walk instability, so we installed variable stiffness mechanism as a head module, only at the head module like this, to control the straight walk instability and bifurcation during experiment. And as a result, autonomous sequential turning tasks were achieved by changing spring compliance to create curved walk with appropriate curvature through pitchfork bifurcation like this. There are many sequential targets, but this can follow the target. just using the change of the dynamics, I mean the bifurcation, by changing the curvature of the behavior. Okay, finally, I'd like to thank you for the collaborators. Thank you very much for your kind attention. Yeah.
Question? Yes, go ahead. The micro, please. Thank you.
Thank you. Really fascinating talk. I have a lot of questions, but I will only ask one. Have you looked at the mechanism that could provide changes into locomotion when you consider bipeds or quadrupeds or multipeds walking in water?
Walking in water.
Yes.
I think that in terrestrial locomotion, gravity is very important because we walk using the kind of the inverted pendulum, and running is a kind of the spring. But underwater, and also we study about the low gravity in the space. In that case, also gait pattern change. Not they use walking, but running very change. It's very difficult to prepare the double support phase because the gravity is very low. In that case, we cannot walk, so we especially use running. But running has also many differences, especially using the different, I mean, the kinematics not so change, but especially the contribution of the muscle change so much because almost the gravity is decreased. So in humans, it's very important to balancing. Balancing is important thing, the contribution to against the gravity. But so low gravity in the space, such kind of the contribution becomes low. So I think the underwater also some similarity between the low gravity on the space, I mean the planet something, on the moon or Mars. Maybe many people will go in the future. Okay.
Professor, really nice talk. I just wanted to know if you only told about torsional springs or springs in general, but most of humans and animals also use damping. Have you considered to use it or implement it in your experiments?
I think especially we use the muscles. Muscle has a kind of the passive spring and also active part. I think the balancing. The kinematics and also dynamics is very important. To simply investigate the contribution of the dynamics, spring is very easy to understand. I mean the very simplest model. Also activity of the muscle can be contributed as the springs. But very, what should I say, to create the locomotion, not only walking and running, the balancing of the dynamics in the passive part and the active part, especially the contribution of the neural system, not only the feed forward, but also the sensory regulation. So I think depending on the study, I mean the locomotion, we have to change especially specific topics. So I think the most simplest case is just using springs, but the spring stiffness and also the, what should I say, the neutral position could be changed by sensory regulations. So such kind of interaction also important. So I think not only the springs part, passive part, but also the active part also important. So yeah, and not only humans. Humans is just against, as I said, just against the gravity. But not only centipede, but the cockroaches do not erect, just only walking on the plains. So I think depending on the situation, I think the important dynamics could be changed. Okay.
Thank you.
Yeah.
More questions? Yes.
Yeah, you have explained several patterns, bipedal, quadruped, and do you have conclusions about what models are better for what uses, or the utility or applicability of each model? So maybe there are, I suppose there are advantages and disadvantages of each type of walking.
So you mean for humans?
No,
For animals.
for
Animals
the-
have
for
many structures.
What are the applications of this? I mean, how to apply, if for
Yeah.
a specific application is better
Yeah.
biped, or for this application is better quadruped, or
Yeah.
whatever. Do you have conclusions about that?
No conclusions, because animals has many varieties. Depending on the structure and also the contribution, such kind of the energy consumption and also stability, depending on the situation, the optimal locomotion type could be different. So I think for humans, we can walk bipedally and also quadrupedally using the forex. But I think we also learned to use bipedally, and it's very, what should I say, it's energy optimal. But it's very unstable. So I think depending on the balancing, stability, energy consumption, and when we walk bipedally, we can use hands. So I think depending on the situation, the optimal gait pattern and the situation could change. I think.
No more question. Thank you so much, Professor Shinya, for your talk.